Okay, this is chapter 6.7, modeling with exponential and logarithmic functions. Essential question says, how can you recognize polynomial, exponential, and logarithmic models? What you will learn in this chapter section is classify data sets, write exponential functions, use technology to find exponential and logarithmic models. Okay, so before I do example one, classifying, how do we classify data? Well, you have analyzed finite differences of data with equally spaced inputs to determine what type of polynomial function can be used to model the data. For exponential data with equally spaced inputs, the outputs are multiplied by a constant factor. So that's the difference between linear and quadratic. If you're doing an exponential, linear and quadratic are a common difference, adding a certain amount each time. In equally spaced outputs are multiplied by a constant factor. So consecutive outputs form a constant ratio, not a constant difference. Okay, so that is how we're going to do these. So we have to look at common differences and see if it's a ratio. So here's example one. So first thing you want to do is you want to look at your input. So that's your x value. -2 to -1 is a difference of 1. We're adding 1, adding 1, adding 1, adding 1, adding 1, adding 1. Okay, so it's a constant change of 1. You want that for when you're getting from one x value to the next. Okay, so step 1. Are we increasing by the same thing? All right, so the inputs are all equally spaced. They're spaced out by 1. And then you look at your y's. Well, what did I do here to get to it from a half to 1? It was an increase by a half. Okay, so 1/2 plus 1/2 is 1. So if I put plus, don't write this yet, I'm just checking. So then if I do 1/2, 1 plus 1/2, I'm going to be at 1.5. So that's not what's happening here. So then I check to see if there's a multiplication difference. Okay, so 1/2 times 2. Okay, so if I multiply by 2, 1/2 times 2 is 1. 1 times 2 is 2. 2 times 2 is 4. And 4 times 2 is 8. And 8 times 2 is 16. And 16 times 2 is 32. So it is a multiple of 2. So since it's a common ratio of 2, I'm going to write that common ratio of 2. Since it's a common ratio of 2, the data in the table represents an exponential function. So this is exponential. Okay, now I'm going to look at this one. To get from -2 to 0, I added 2. 0 to 2 is 2. 2 plus 2 is 4. 4 plus 2 is 6. 6 plus 2 is 8. 8 plus 2 is 10. So the first thing you want to do is check to see if your input is equally spaced, and it is. And then you're going to look at from 2 to 0, I would subtract 2. I'm always going to check my use addition and subtraction and check it first. So -2, I subtract 2 from 2 to get 0. 0 minus 2 is -2, but that's not what I got here. So now I know it's not a subtraction problem. So what I'm going to do is just write what the change is. So that's a change of down 2. That's a change of +2. Then it's going to a change of 4. Okay. And this is a positive change of 10. And this is a positive change of 14. And this is a positive change of 18. So this is a difference of 4. This is a difference of 2. And this is a difference of 6. And then 4. And then 4. Okay, 18, 14, 10, 6, 2, -2. So then what I'm going to do is check the second difference. So from -2 to 2 is 4. Oh, I made a mistake here. This is 6. I just saw 2 plus 4 is not 8. So let me go back and change my color back to green. This is a difference of 6. Okay, so this went down 2, and this went up 2, up 6, up 2. Or from 8 to 18 is 10, 18 to 32 is 14, and 32 to 50 is 18. So this is a difference of 4. From 2 to 6 is 4. From 6 to 10 is 4. From 10 to 14 is 4. And from 14 to 18 is 4. So this is the second difference. Okay. And since the second differences are constants, the data in the table represents a quadratic. Okay, we didn't get a common multiple. 2 times something does not give me 0. 0 times that same something. Since there's a 0 in there and it went down and then back up, that is a quadratic function. If the common ratio is 2, we multiply by 2 times 2 times 2 times 2. This is getting multiple. The multiple is increasing exponentially. Then it becomes an exponential function. But in this case, it is increasing by a second difference of 4. And therefore, that is a quadratic from prior chapters. So at this point, you should be able to do problem numbers 3 and 4 in the exercises. Okay, example 2 is writing an exponential function using 2 points. So it says write an exponential function y equals a times b to the x whose graph passes through the point 1, 6 and 3, 54. So here's what we're going to do. We're going to write the function. Step 1, you just write y equals a times b to the x. So I'm going to do this in red. So this is my x and this is my y. Now I'm going to substitute it in. 6 equals a b to the first power. Okay, so that's the first step. The other thing you want to do is then do the same thing for this function. So I'm going to write y equals a times b to the power of x again. My y is now 54 equals a times b cubed. Okay, my x is 3. All right, so then you want to come back to the first problem and you want to solve for a. You want to get a by itself. So in order to solve for a, you're going to divide by b. Well, b to the 1 is just simply b, so it's going to be 6 divided by b, and these cancel. And we get a equals 6 over b. I then take this a value and substitute it into my other equation for a. So it's going to be 54 equals 6 over b times b cubed. And I'm just going to put this over 1 just so you can see what's going to happen here. And I'm going to simplify. 54 equals, well, this b is going to cancel one of these b's, so that's going to drop that down to b squared. And now I just have a 1 in the denominator, so when you divide by 1, you get the numerator, so it's just going to be 6b squared. Divide both sides by 6, I'm solving for b, and these cancel, and I get b squared equals 9. And then I take the square root of both sides to find b, and b is going to equal 3. Now remember, when we take the square roots, it's plus or minus the radicand, but I can't have a negative b when I'm doing exponential functions. So b equals 3. Okay, so now once I get b, now I can find a. Now I'm going to go back to this problem here, and I'm going to substitute in b here. So it's going to be a equals 6 divided by b, which is 3. So therefore, a equals 2. So now my exponential function is going to be y equals 2 times 3 to the x. And there is my exponential function. Okay, so that's how you find the function. And now let's check it with our calculator, actually. So I'm going to open my calculator up. I'm going to clear. I'm going to hit y equals. I'm going to put 2 parentheses 3 to the x. Whoops, I forgot, to the power of x. So 2 times 3 to the x, and I'm going to zoom 6 that. And I always start with that. But keep in mind, I have a 0.3 comma 54. So now I want to change my window to my y max to be over 54. So how about 60? And hit graph. So now the function's coming over. There it is right there. And I really don't need to go below the y-axis. So I'm going to make my y minimum 0. And I can make this -5. And how about I go out to just 5 on the x? So you just play around with your window, and here's what you get. So that's a much nicer fit. And then I'm going to check to see if the 0.16 is there. So I'm going to hit second, calculate a value, and I hit 1, enter. And when x is 1, y is 6. That worked. And then I'm going to hit second, calculate a value, and I want to know when x is 3, if y is in fact 54, and there it is. So that's a way of checking. So that confirmed that this is the exponential function that goes through the 0.16 and the 0.3 comma 54. So now you should be able to do problem number 7 and 8 in the exercises. Okay, example 3 is finding an exponential model. So we're told it's exponential, so we want to look for an exponential model. It says a store sells trampolines. The table below shows the numbers y of trampolines sold during the first 7 years. The x years of the store has been open, the first 7 years. Okay, write a function that models this data. So I'm going to do a different set of numbers, but the first step in doing this is to draw a scatter plot. So instead of drawing it, I just brought the picture in from the book. And this is the 0.112, 216, 325, 436, 550, 667, and 796. Okay, so the book chose the 2 points 12 and 36. 112, 436. So the book chose this number, this set of numbers, and this one. And the reason they did was because 36 divided by 12 is 3. Just to be different, you can choose any of the two for an approximation. So I'm going to choose these two just to be different than the textbook example. I'm going to choose 216 and 550. So in order to find an exponential model going through 2 points, so I am choosing, let me show it on the table. I'm showing the point 216, which is here, and the point 550, which is here, instead of the book using 1 and 3. The book was using these two. I'm using these two. All right. So first thing you do is write the function y equals a times b to the power of x. Y is 16. Equals a times b to the power of 2. I'm also going to write this again, y equals a times b to the x, but now y is 50. A times b, and x is 5. So these are our two functions, okay? So I'm going to solve for a in the first one. So I'm going to divide by b squared. Divide by b squared. So that's going to give me a equal to 16 divided by b squared. Okay. I am then going to take this 16 over b squared and substitute it in for a in the other equation. This is going to give me 50 equals 16 divided by b squared times b to the 5th. And I'm going to put that over 1 just so you can see what's happening here. And b to the 5th divided by b squared, you subtract your exponent. So get rid of 2 of the b's, and you're going to be ending up with b cubed. So 50 equals b cubed. I'm sorry, I almost forgot my 16. The 16 is still there. 16 b cubed. Divide both sides by 16. These go away, and I'm going to get b to the 3rd power equals 50 divided by, that's a 0. 50, let me fix that. 50 divided by 16. Okay. So b cubed is 50 divided by 16. I want to find b. So I'm going to take the cube root of both sides. And I'm going to get b is approximately, and I'm going to go over to my calculator. And I want a cube root of 50 over 16. So I go to math, and cube root is 4. So there's the cubed root of, and in parentheses, I'm going to put 50 divided by 16. And I'm going to hit enter. And it's 1.462 is close enough. So 1.462 is my B. So now that's going to go in over here. So now A equals 16 divided by 1.462 squared. So A is going to equal 16 divided by my answer, which is down here. And if I do second answer, it's going to keep that 008869. So it's going to be more accurate than just rounding like I did drawing it over here. And then I want to square that. So it's 16 divided by the answer squared, and 16 divided by 1. Let me do this. Let me do it this way. Let me go up to here and get that 1.462 and square it first, just to make sure the parentheses are in the right place. So it's 2.137. So this would be 16 divided by 2.137. So A is going to be approximately, and this should be an approximation. So now I'm going to take 16 divided by this answer, and to do that in the calculator, hit 16 divide second answer. The ANS here will give me this number here, and I hit enter, and I get 7.485. Okay, so there is my A. Okay, so if you were looking at the book while doing this, they got an answer as, so I'm going to write my answer now. I get a function that says y equals A times B to the power of X. This is the equation I came up with using 216, 550. The book says y equals 8.32 times 1.44. So their A is bigger, but their B is smaller. So this is an approximation. This should still give us an approximate correct value. So when I put this in as 7.485 parentheses, 1.462, close the parentheses, to the power of X, and I go to my window, notice my window's going from 1 to 7 on the X. So how about I do -1 so I can see the Y-axis, and leave that 10, or maybe just go to 8. And then my Y minimum, I don't care about anything in the negatives, but if I put -1, I'll be able to see my X-axis. And my biggest number is 96. So how about I go a little bit higher to like 100, and then I hit graph. So here's the function coming up. And sure enough, it goes up and everything is on the screen. Beautiful. Now I hit second calculate, and I want to check 1. I want to know what the value of Y is when X is 1. And I got 10.94, which is about 11, and they got 12. Now, if I do second calculate 2, second calculate, enter, and plug 2 in. When X is 2, Y is 16. And look at this, 15.998, very close to 16. I'm going to keep checking. Second calculate a value when when X is 3, Y is 23. This is 25. So it's still pretty close. Second calculate a value and check 4. When X is 4, Y is 34. Well, we have 36. So it still is a little lower, but it's close. Second calculate a value. I want to know what 5 is. When X is 5, Y is 50. And look at that, it's off by a really small margin. And then second calculate a value. When X is 6, Y is 73. That's a little high. And then second calculate a value. X is 7, Y is 106. So doing my calculation and the way it rounded, it was a little low until it got to my point that I used, but then it was growing faster. But it is a close approximation. So no matter what two numbers you use, you're getting an approximate function that fits the data. Okay, so now that we've done this example together, you should now be able to do number 19 in the exercises. Okay, example 4 is writing a model using transform points. Okay, so it says use the data from example 3. So I brought that data in. If you don't remember, that was the trampoline company, the store that sold trampolines for 7 years and how many trampolines they sold. So there's the data set from example 3. And they want us to create a scatter plot from the data pairs, but they want us to do x comma the natural log y to show that an exponential model should be a good fit for the original data pair x comma y. These are original data set x comma y. Then write an exponential model for the original data. So what they're telling us is, what they're talking about is they want to know if r is close to 1. Okay, if your regression line is close to 1.0, that's the best fit you can get. If r equals 0, then it's not linear. So if we graph this function as x comma the natural log of y, we're checking to see if r is close to 1. If it is a straight line, then it is a good representation of the data. So that's what we're talking about here. All right, so what we're going to do is we're going to do a table. So we're going to create a table of the data pairs x comma the natural log of y. So here my x is 1, 2, 3, 4, 5, 6, 7. So I'm going to put those in here. So there's 1 through 7. And then I'm going to use my calculator to do the natural log of y. So when x is 1, y was 12. I want the natural log of y from over here. So I want the natural log of 12. And that is 2.48. So there's 2.48. Then I want the natural log of 16. And that's 2.77. Then I want the natural log of 25. So we just keep doing this. And that's 3.22. Watch how you round. 3.22. Natural log of 36 is the next one. And that is 3.58. Okay. And then the natural log of 50. Okay. So that's 3.91. Natural log of 67. And that is 4.20. And the natural log of 96. And that is 4.56. Okay, so that's the first step. So we created this data, 1, 2, 3, 4, 5, 6, 7. Then we took the natural log of these y values, and now we have these values here that we're going to plot. So step 2 is, whoops, I'm skipping there. Step 2 is plot the transform points as shown. The points lie close to a line. So an exponential model should be a good fit for the original data. So what they're saying is when we graph this, we got the point 1 comma 2.48. And these are all the points from here. And they're really close. These two are a little bit above. This one's a little bit below, but they're really, really close to a straight line. So that means that our r is very close to 1. So r is probably 0.96 or something like that. So this proves that the natural log function is a good fit for our original data. So then what we want to do is we want to find an exponential model y equals a times b to the x by choosing any 2 points on the line, such as the first one, 1 comma 2.48, and the last one, 7 comma 4.56. We're going to use those points to write an equation of the line and then solve for y. So step 1, this is what they wrote in the book. And I'm going to explain because they skipped some stuff. They're going to assume now that you know this, but I'm still going to show you in the video. Where did this equation of this line come from? Well, the equation of a line is y minus y1 equals the slope times x minus x sub 1. That's the point slope formula. We have points, we can find the slope, and so I need to find the slope. The slope is y2 minus y1 divided by x2 minus x sub 1. So that's going to be y2, 4.56, minus 2.48 over x2, 4.5, oh, I'm sorry, x2, 7, minus x sub 1, which is 1. So this is going to simplify to 7 minus 1 is 6. 4.56 minus 2.48 is 2.08. So therefore, our slope is going to be 2.08 divided by 6, which is 0.35 approximately. So I'm going to make that an approximation, and it's 0.35. And as you can see, that's right there. Okay, so that's how they got that slope. So y is the natural log of y now. So this is my y right here. This is y minus y1. Okay, see how it's coming together now? Y minus y1 equals the slope m, which I just showed you how to find over here, times the quantity in parentheses of x minus x sub 1, which is 1. So it's minus 1. So that's where this equation came from. So then the book shows this next step. It says simplify. Well, they're skipping some steps here, so let me show that. So if I have the natural log of y minus 2.48 equals 0.35 times x minus 1, what they're doing is they're distributing this 0.35. So this would be the natural log of y minus 2.48 equals 0.35 times x minus 0.35 times 1, which is 0.35. And then they add 2.48 to get the natural log by itself. So add 2.48 to this. And when I do that, these cancel and I get the natural log of y, which is right here, equals 0.35x, which is right here, plus 8 minus 5 is 3, 4 minus 3 is 1, 2 minus 0 is 2, and that's where this all came from. Okay, so they just skipped some work and just cut to the chase. They simplified, and that's that. So now what we want to do is we want to take base e of both sides. Since there's a natural log on one side but not the other, if you take the base e of both sides, you get rid of the natural log. So this is the next step the book is showing, but they are not, what they aren't showing is what they did. So they're going to do e to the natural log. Actually, let me just do it like this. What they basically did was just took the base e of this side and the base e of this side. So e to the natural log of y equals e to the this. Remember that e to the natural log is base e, so those cancel, leaving me with y equals e to the 0.35x plus 2.13. And that's how they got this. Then they're going to show you in the book that they did the properties of exponents. Okay, so it's the properties of exponents. What they're saying is when this is a plus sign, you can then state that e to the 0.35 and then multiply it by the same base of 2.13. And that's what they're showing here. I forgot my x. 0.35x plus e to the 2.13. Okay, when you see a plus sign, you can multiply and show the e twice. That's what they did here. So I can find e to the 2.13. So then the book is showing this step, and they aren't explaining where it comes from. So watch what I'm going to do. I'm going to do second natural log to get e to a power, and I want e to the 2.13. 2.13, hit enter, and I got 8.41, and that's where that came from. So it's y equals 8.41, which came from this component, and then it's e to the 0.35. Now, e to the 0.35x can be written as e to the 0.35, okay? And then you can put the x outside like this. That's what they're doing here. So then I'm going to take e to the power of 0.35, and that is 1.419, which rounds to 1.42. So that is how they got to 8.41 times 1.42 to the power of x. So here's my a, and here's my b. So now I have it an exponential equation. Okay, so that is it simplified. So an exponential function that models this data, since it was a line when we did the x comma natural log function, we realized that r was close to 1 because that's almost a perfectly straight line. So since it is, we use the linear equation to find a model of a function for that data. So the data is 8.41 times 1.42 to the power of x. Okay, so now that we've done that, you should be able to do problem number 25 in your exercises. Okay, example 5 is finding an exponential model. It says to use a graphing calculator to find an exponential model for the data in example 3. So again, here's the data in example 3. Here's my calculator. So in how you do that is you turn it on. You press the stat button. This brings you to this screen. You want to leave it where it is. You want to edit the data by entering it into a table. And if there's some data here, let's just say there was 5, 6, 7, 10, something like that. If you want to get rid of that, all you do is go up until your cursor is over L1. You hit clear and you arrow down. So it's empty. Okay, just want to make sure that's empty. Now I want to enter this data 1 through 7. So I'm going to hit 1, 2, 3, 4, 5, 6, 7. Okay, then to get to L2, you arrow to the right. So now we're up, the cursor's over here next to 1. Well, what was y when x was 1? It was 12. So I want 12, 16, 25, 36, 50, 67, and 96. Okay, so I just entered all of that data. And now I want to calculate a regression, okay? So it says use a graphing calculator to find an exponential model. So the first thing I want to do is I want to highlight that. That is what we are trying to do with our calculator. So I'm going to hit stat. Now I arrow over to calculate. And these are all the different types of models the calculator will do. They told us to do an exponential regression, which is 0. So I had to scroll down, calc 0, hit enter. Now it's saying X list is coming from L1, Y is coming from L2. So all you got to do here is just enter through. And when you get to calculate and hit enter, it will calculate your equation. So A is 8.45. So then you take your equation and you just write it out. Y equals A, which is 8.46, times B, which is 1.42 to the power of x. Okay, and that's what they're showing in the book, I believe. Let me take a look. Example 5, and it is 8.46 times 1.42 to the x. That's the regression model. Okay, so in the book, they're showing a few things. Now, the other thing I wanted to mention to you here is how do you know if this is a good fit? Well, if you press the second button and you look at 0, see the catalog in blue here? So if I hit second 0 for catalog, and just to speed things up, I'm going to go to, whoops, not second, I want alpha, I want D. So where is D? A, B, C, D. I'm looking for green D, which is right here. This will jump to D, and I arrow down. What am I looking for? I'm looking for something that says diagnostic. There it is. Diagnostic off, diagnostic on. So I'm going to hit enter twice to turn the diagnostic on. And then I'm going to go back to stat, calculate 0 for the regression. And I'm going to enter through again. And now it gives me my R and my R squared, my regression. So notice that it's 0.998. That's really close to 1. And that's what we showed in example 4 with this equation right here. That is almost close to 1, which means it is close to the best you can get, which is a line. If R equals 1, it is a perfect line. Okay, so that's what I was trying to explain there. So now that we're at this point, what's next? Okay, so I use my regression equation, and it's y equals 8.46 times 1.42 to the x. So example 3 said, if we go back, example 3 was here. Now my numbers are different than what the book had because I chose two different points than the book, but it's similar. The book had 8.32 times 1.44 to the x. And example 4 had 8.41 times 1.42. So here's example 3, here's example 4, and here is the equation I got when I used the regression model from example 3. Okay, so that's what they wanted us to do. It said use the model that modeled in example 3 and 4 to predict the number of trampolines sold in the 8th year and compare your predictions. So all they're wanting us to do now is calculate y equals 8.46 times 1.42 to the power of 8. And then down here, they want us to do y equals 8.32 times 1.44 to the power of 8. And then finally, what they want us to do, y equals 8.41 times 1.42 to the power of 8. So I'm going to put that in my calculator. So I'm going to put 8.46 parentheses 1.42 to the power of 8. Oops, I forgot my close parentheses. Okay, so put a parenthesis there and delete. There, okay. So that is 8.46 times 1.42 to the 8. That's this one. And so this one is going to be approximately 139.85. Okay, you can't sell a part of a trampoline, so let's just round to 140 trampolines. Now I'm going to do 8.32 parentheses 1.44, close the parentheses, to the power of 8 and hit enter. That is 154, roughly 153.8, 154 trampolines in the 8th year. And then finally 8.41 times 1, I want parentheses, 1.42, close parentheses, to the 8th and hit enter. And that one I got approximately 139 trampolines. Okay, so that is what they wanted us to do in example 5. So the predictions are close for the regression model and the model in example 4 that use transform points. These predictions are less than the prediction for the model in example 3. So then you're just summarizing your results. Okay, so there's example 5. Now you should be able to do problem number 31 in the exercises. Okay, example 6, finding a logarithmic model. So it says the atmospheric pressure decreases with increasing altitude. At sea level, the average air pressure is 1 atmosphere. That is 1.033227 kilograms per square centimeter. The table shows the pressure P in atmospheres at selected altitudes H in kilometers. Use the graphing calculator to find a logarithmic model of the form H equals A plus B times the natural log of P that represents this data here. And then estimate the altitude when the pressure is 0.75 atmospheres. Okay, so that's what we need to do. Pretty straightforward, simple. So here is a weather balloon. That looks kind of familiar. What's it doing up here? Okay, China. Yeah, it's really interesting that they have a weather balloon problem in this. And it lines up nicely with the news right now. So anyway, here we go. Here is my calculator, and I turn it on and I clear it. I go to y equals, there's nothing there. Very good. Press stat, edit, and my last problem is still in there. Arrow up to L2, hit clear, arrow down, arrow over, arrow up to L1, press clear, come down. And now I want to enter this data. Air pressure P is my L1. So I'm going to put 1 and then 0.55. 0.25. So as we go up, the pressure decreases 0.12, 0.06, and 0.02. Okay, so there's our X's. Oops. cancel. Go back here, clear. Arrow over, arrow up, arrow over. Okay, 0.2 is the last one. And then I want to put my y's in. L2 is 0, enter, 5, enter, 10, 15, 20, 25. Okay, so this is just a practice on entering data in your calculator and coming up with a regression model. This time I want a logarithmic model. So then I go stat, calculate. Okay, so linear regression, quadratic, cubic, quartic, linear regression, ln regression. There is a log, natural log, okay? And then I'm going to go to, ln regression. So it's not exponential, it's logarithmic. So there's natural log regression, and I'm going to hit enter. I want my data to come from L1 and L2, so I just enter all the way through. I already turned my, what was it called? Diagnostics on. And as you can see, it's R squared is very close to 1. R is very close to -1. Okay, so it's decreasing. As the altitude goes up, the air pressure is decreasing. So it's very close to a linear model. So it's a good fit. That's what that means. Okay, so there's my equation. So I'm going to write that. So let me get my pen. And I want H equals A plus B times the natural log, times the natural log of P. So it's going to become H equals, A is 0.8626, so that's going to round to 0.86. So how about just putting 0.86 plus my B? It's not plus, it's negative, so it's minus. I don't ever want to write plus a negative, just put minus 6.4. 6.4 and 7 makes the 4 a 5, round to 2 decimal places. And then the natural log of P. So there's my equation. H equals 0.86 minus 6.45 ln of P. P is our pressure. Then it says estimate when P is 0.75. So what I want to do is I want to find H in this equation. So H equals 0.86 or 0.86 minus 6.45 times the natural log of 0.75. So let me change colors for that. I'll make it green. 0.75. All right, so that's what I'm putting in my calculator. So I could do this a couple of ways. I'm going to show you in the calculator using the graph, but then I'd have to adjust my window. If I graph that, okay, I don't see anything because X goes from 1 down to 0.2, but altitude H is 0 to 25. So window, I want my X to go from 0 to 2. Okay, or 0 to 2, just so I can see 1. And I want my Y minimum to be 0 and my Y maximum to be 30, just so I can see 25. Now I'm going to graph this. And as you can see, I don't see anything. So if I go back to Y equals, I have to put that equation in there. So if to do that, I go to Y equals, I want my plot on. Okay, arrow down, and I hit vars and 5 for statistics, arrow over to EQ, and it says regression equation, and I hit that and I hit graph. Okay, so there's my model. So as altitude increases, pressure decreases, just like we're seeing. Now we can do an approximation and see what 0.75 is. So then I could hit second, calculate a value when X is 0.75. What is the function value? So it's 2.717. Okay, so then I could say H is approximately 2.72 atmospheres. Okay, 2.72. So that means when the air pressure is 0.75 atmosphere, the altitude is 2.7 kilometers. So h is height or altitude. So this is kilometers. So the answer is 2.72 kilometers above sea level. Okay. The other way I could have done it is just gone to my home screen and done 0.86 minus 6.45 natural log 0.75 and hit enter, and I get the same number. Okay, but I just wanted to show you the graph and how it is a regression natural log function coming down, approaching 0. Okay, so now that I've done example 6, you should be able to do problem number 33 in your exercises. All right, that brings us to the end of chapter 6.7. Do these problems, and since there's only a few problems, what is there, 7 problems? 8. I threw in 3 review problems. Okay, thanks for watching and have a great day.